Hello friends, welcome to DCBA, and in this lecture we are going to solve a indeterminate or a continuous beam problem using stiffness matrix method. As you can see here, this is a beam with different moment of inertia. That is, for span AB it is I, and for span BC it is 2I, and 2 point loads, one concentrated moment and one UDL. So let's get started. Step 1 is to draw positive forces and moments at each joint. And if you've seen my previous video, you might already know what are positive forces and moments in stiffness matrix method. And these are the positive forces and moments, that is, forces which are aligned in the direction of the Cartesian coordinate axis. Now these we have to solve using beam element, and for beam elements we have only two forces, that is, one is a upward force and another is a moment. The double arrows show the moment which are acting in the z axis. This is the z axis, this is the y axis, and this is the x axis. So there is no force acting in the x axis, and we have to draw forces at each joint, that is a, b, and c. So at all the joints we have to draw the positive forces. Upward force in the direction of y axis, and a double arrow, that is moment, in the direction of z axis. Now these movements are, the direction of these movements are given by right hand thumb rule, that is thumb pointing in the direction of the double arrows and the curl of the finger showing the direction of the moment. That is, this is an anti-clockwise movement, and anti-clockwise movement at every joint is positive and upward force at every joint is positive. So these are our positive forces and moment at each joint. Step 2 is to number each force and beam appropriately. Numbering is very important, because the stiffness matrix that you will be forming later on, the stiffness matrix that you'll be using to solve this sum, will depend upon how this numbering has been done while deriving the stiffness matrix itself. So if you've seen the video of deriving stiffness matrix for a beam element, you must have seen that the numbering in beam element was done as the upward force having the first number and then the moment. Similarly, here, the upward force then moment, the upward force then moment. So 1, 2, 3, 4, 5, 6. This is very important, okay? You have to write the numbers this way only. You cannot interchange the numbers. If you interchange the numbers, then your matrix will get interchanged. And you cannot use the matrix that I'll be using in this sum. So the numbering has to be done this way. First the upward force, then the moment. Now after you have numbered each force, step 3 is to assemble the total stiffness matrix. Now I have just minimized my structure here for your reference. All the positive forces are there, and now we'll assemble the total stiffness matrix. And total stiffness matrix is given as stiffness matrix for element 1. This I'll say as element 1, that is AB, plus stiffness matrix of element 2. I'll say element 2 as BC. So the total stiffness matrix is stiffness matrix for this beam plus stiffness matrix for this beam. So first we'll write stiffness matrix for element 1. K1 is 12 EI by L cube, 6 EI by L square, 6 EI by L square, 4 EI by L. And if you've seen my previous video, I have already shown there that how to remember this matrix. These four elements will be repeated again and again, except the last corner one. They will be interchanged. And the signs, how to write the signs, also I have mentioned in that video, so you can just check it out. And this is my stiffness matrix for element 1. Now we need to substitute appropriate I, that is, for element 1 I is I only, and L is 3, that is 1 plus 2 3. So we have to substitute the value of I and L, and then we get the matrix as 12 EI by 27, that is L was 3, so 3 cube is 27, 6 EI by 9, 6 EI by 9 again, 4 EI by 3, and then we need to copy all these elements here appropriately. Once you have finished constructing the stiffness matrix for element 1, I will suggest you to write these numbers also, 1 2 3 4, 1 2 3 4. How did these numbers come? These are basically the force numbers, that is 1 2 3 4. So for beam 1 or for element 1, these are the forces that we are considering, 1 2 3 and 4. So in line, going from ascending order, 1 2 3 4, 1 2 3 4. Okay. And these numbers are very important in the later stage because they act as reference points. Stiffness matrix for element 2 will also be the same. It is same as what you have seen previously, and just notice these numbers. Now they are 3 4 5 6 and again 3 4 5 6. Why they are 3 4 5 6? Because for element 2 it starts from B, and B has numbering as 3 4 5 6. For element 1 it was 1 2 3 4. For element 2 it is 3 4 5 6. That is why I have written here 3 4 5 6 and the inner elements as it is. Now we have to substitute the values of L and I appropriately. I is 2I and L is 4. So substituting these values we get 24 EI by 64, because I was 2I, so 12 EI became 24 EI, and L was 4 cube, so it became 64. 12 EI by 16, 12 EI by 16, 8 EI by 4. And then again copying these values appropriately with all the sign conventions, we get the whole stiffness matrix. Now we need to get the total stiffness matrix, which is stiffness matrix for element 1 plus element 2. So we have here total stiffness matrix as K and K1 plus K2, and now we have to write them properly. The total stiffness matrix will be a 6 cross 6 element, because here there are 6 forces, 1 2 3 4 5 6. Thus it will be a 6 cross 6 element matrix, and you need to substitute the elements appropriately now. First is 1 1, that is 1 1 element, 12 EI by 27. Then 2 1, that is 2 1 element, 6 EI by 9. Then 3 1 goes into the place of 3 1 minus 12 EI by 27. Then 4 1 comes from this 4 1, 6 EI by 9. Now if you see 5 1, there is no 5 1 element, because even in both the matrix there is no 5 1 element, so it is 0. Again there is no 6 1 element, hence it is 0. Now we'll come here 1 2, that is I hope you know how to number the matrix. That is, first is row number, then the column number. So row number comes first. This is first row, second column. Therefore, it is called as element 1 2. So element 1 2 is 6 EI by 9. Then element 2 2, row, second column. Element 2 2 is 4 EI by 3. Element 3 2, third row, second column, minus 6 EI by 9. Element 4 2, fourth row, second column, 2 EI by 3. And then there is no element at 5 2, nor there is element at 6 2, so 0 0. Now we'll write element 1 3, that is first row, third column, minus 12 EI by 27, minus 6 EI by 9. And now element 3 3, element 3 3 is common in both the matrices. That is, element 3 3 is also occurring here, and it is also occurring here, so we need to add them up. Element 3 3 needs to be added up. So 12 EI by 27 plus 24 EI by 64, I get 59 EI by 72. Again element 4 3, that is fourth row third column is occurring in this matrix as well as it is occurring in this matrix. So fourth row third column is, in this matrix it is minus 6 EI by 9, in this matrix it is 12 EI by 16. So we need to add them and we get EI by 12. If I just add this element and this element, I get EI by 12. Fifth row third column is, fifth row third column, there is no fifth row third column in matrix 1, but there is fifth row third column in matrix 2. So it is minus 24 EI by 64. Sixth row third column, not in matrix 1, but it is in matrix 2, 12 EI by 16. So as per, like, what I suggest you is that for every element, when you write starting from element 1, you just search that element in both the matrices. If it is present in matrix 1, is it present in matrix 2, or is it present in both the matrix? If it is present in both the matrix, you need to add them. If it is not present in only one matrix, you can write it as it is. So I hope how to complete this whole matrix. Element 1 4, Element 1 4 is present only in matrix 1 and it is not present in matrix 2, so it is 6 EI by 9. Element 2 4 is present in matrix 1 only, not in 2, so it is 2 EI by 3. Element 3 4 is present in matrix 1 as well as in matrix 2, so we need to add them up. So it is EI by 12, that is adding up this element and this element 3 4, third row fourth column, third row fourth column. Element 4 4 is also present in both the matrix, that is fourth row fourth column, fourth row fourth column. We get 10 EI by 3. Then we have fifth row fourth column, that is it is only present in matrix 2. Fifth row fourth column minus 12 EI by 16. Sixth row fourth column 4 EI by 4, present only in matrix 2. Again, first row fifth column there is no element, as first row fifth column, therefore it is 0. Second row fifth column is also no element, hence it is 0. Third row fifth column is present only in matrix 2. Third row fifth column minus 24 EI by 64. Fourth row fifth column minus 12 EI by 16. Fifth row fifth column 24 EI by 64. Sixth row sixth column minus 12 EI by 16. First row sixth column 0. Second row sixth column 0 because both these elements does not exist. Third row sixth column is 12 EI by 16. Fourth row sixth column is 4 EI by 4. Fifth row sixth column is minus 12 EI by 16 and sixth row sixth column is 8 EI by 4. Now that's very interesting thing about this matrix, that this is symmetric about the diagonal elements. Okay, it is this triangle, the lower half triangle or the upper half triangle are symmetric elements, that is element 1 2 1 2 is symmetric to element 2 1, both are similar, these both are similar, then these both are similar, these both are similar, that is element ij is equal to element ji. Okay, element ij, that is first row second column, is equal to element ji, that is element 2 1, second row first column. Element 3 4, that is third row fourth column, is equal to element 4 3, fourth row third column. So the lower triangle is equal to the upper triangle except the diagonal elements. Diagonal elements are different, only the lower triangle and the upper triangle are similar. So if you just complete the lower triangle or the upper triangle, you can automatically fill the rest half. Okay, so you don't have to completely fill all the 6 by 6, that is all the 36 elements. You can fill half of this matrix and then you can copy it as per their numbers, as per their positions. This is completing our step 3, that is total stiffness matrix. Next step is to construct the joint load matrix. Now what is joint load matrix? It is the matrix at every joint, that is A, B and C, and if there exists any load at any of the joint. So if you can see, there is no load at joint A, no load at joint C, but there is a load as well as a moment at joint B. So this is how we constructed 0, because 0 load in the direction of 1 first force, 0 again because 0 moment in the direction of 2 third. Third is a upward force, and as you can see there is an upward force here 40, so it is plus 40 because it is acting in the direction of 3 and at joint B. And fourth, there is again a moment at this joint, but if you see this moment, the fourth moment is an anti-clockwise and this is a clockwise moment, so it has to be written as negative because our positive force is anti-clockwise, right? These are the reference forces which needs to be positive. So if there is an upward force, that is, it is a positive force. If there was a downward force here, then it would have been a negative force. Similarly, if there was an anti-clockwise moment here which meets with a reference moment that is also anti-clockwise, it would have been positive, but here it is clockwise moment, so hence it is negative, therefore minus 10. Then again no force here in the upward direction, 0, no moment in the z direction, hence 0. This is my joint load matrix, which I'll call it as AJ. Okay. Step 5 is member reaction matrix, AR. It is called as AR, and AR is given as AR1 plus AR2. Again, AR1 for element 1, AR2 for element 2. So what is member reaction matrix? I'll show you here. Member 1 is this AB, which will give me my AR1, and I've drawn your member AB with all the positive forces, and this is my load that is acting 80 kilonewton. So what I basically need to do is I need to find the reactions because of this load. Okay. And the reactions because of this load would be two moments, that is one moment here, and two forces, that is two reactions, right, at both the ends. So moment I can find as these are first of all reactions, that is two moments and two reactions, reactive forces upwards, and moment is given as WAB square by L square. It is a fixed end moment due to a point load acting at distance A, which is given as WAB square by L square, which is equal to 35.56, and here it is WBA square by L square, which is equal to 17.78. I hope you know about the fixed end moments by now, because that is the prerequisite for everything. And the reactions can be found by simple equilibrium conditions. That is, if you take the summation of moment A equal to 0, then you can find this particular reaction, and then from summation Fy equal to 0, you can find this reaction. We need to construct our AR1, that is AR1 matrix, and similar to how the joint load matrix was, that the loads which were acting at the joint in the direction of 1, 2, 3, and 4, we need to write here. So here, instead of loads, we are writing the reactions formed due to this particular force acting. So in the direction of 1, it is 59.26, and both the directions are same, therefore it is plus 59.26 here. Then 2 is a moment, and this moment is also anti-clockwise. Our positive moment is also anti-clockwise, hence it is conforming with it, therefore it is plus 35.56. Third force is number 3, is a force which is acting upwards. This force is also acting upwards, hence it is positive. And number 4 is a moment, again acting in the anti-clockwise direction, which has to be positive. Here, if you see, then this moment is acting in the clockwise directions, hence it does not conform with our positive reference moment, therefore it is negative, minus 17.78. This constitutes our AR1 matrix. Now we'll come to AR2 matrix, again doing the same thing, that is we need to find the moments, two moments and two reactions. This has to be much simpler because it is symmetric. The load is symmetrical on the whole, or the load is acting on the entire complete beam, therefore it is symmetric on both the sides. Therefore the moments as well as the forces will have to be equal. The moment is given as WL square by 12, fixed end moment, which is equal to 66.67 kilonewton meter, and the upward force is given as 15 to 4 by 2, that is 100. And we need to construct the AR2 matrix, and now the numbering will be 3, 4, 5, 6, because the forces are 3, 4, 5, and 6 for member 2, and the force acting in the direction of 3 is 100 plus 100 because it is acting in the same direction. The moment in the direction of 4 is again anti-clockwise, which meets with the reference moment, and it is plus 66.67. So force 5 is again a upward force, which is 100, acting in the same direction as this positive force, therefore it is plus 100. And number 6 is negative because it is a clockwise moment and it does not conform with our positive reference moment, therefore it is minus 66.67. Now we need to add both these, and the final AR matrix would be a 6 element matrix, 6 cross 1 matrix. The first element will be 59.26, second is 35.56, third is common in both the matrix, that is AR1 and AR2, therefore we need to add them. So 100 plus 20.74 will give me 120.74. Again, 4 and this 4. Both are common in both the matrix. Therefore, we need to add them. It will give me 48.89, and fifth element is 100, sixth element is minus 66.67. Step 6 is to find the combined load matrix, and combined load matrix is denoted as AC, and AC is equal to AJ minus AR. Very simple, AJ minus AR. The AJ matrix was this, AR matrix is this. We need to just subtract them. Simple subtraction of matrices, which will give me 0 minus 59.26 is minus 59.26. Again, this is minus 35.56. 40 minus 120.74 is minus 80.74. Minus 10 minus 48.89 is minus 58.89. 0 minus 100 minus 100. 0 minus of minus 66.67 is plus 66.67. This is my combined load matrix, and we will use this to find the unknowns, that is dk. Now, assemble stiffness equation is our seventh step, and this is my stiffness equation, that is total stiffness matrix into the delta, that is unknown matrix or the displacement matrix, is equal to AC, that we just found in the previous step. K, the total stiffness matrix, was found in the step 3. This is my deflection matrix, that is the deflection at every joint, delta A, theta A, delta B, theta B, delta C, theta C. Delta A and theta A act at joint A, delta B, theta B for joint B, delta C, theta C for joint C. Okay, and it is equal to my AC matrix that we found previously. Now, this is very important here, that we need to know the conditions of every joint here. And as you can see that delta A, which is the deflection at A, joint A in the upward direction, has to be 0 because this is a fixed joint, right? And there cannot be a upward deflection at a fixed joint. Therefore, this whole thing goes row 1 and column 1. Okay, because this cannot occur, that is delta A cannot occur, therefore we need to cancel it out. Row 1 column 1. Again, theta A cannot occur because there is no rotation at a fixed joint. My A is fixed and there is no rotation at a fixed joint. Therefore, again 2, row 2 column 2. Now delta B. Again, this is a support, a roller support, and there is no vertical displacement for a roller support. Therefore, 3, 3. Theta B will occur because this is a roller support, and once it is deflected, there will be some rotation at this point. Therefore, theta B will remain, and we won't cancel it out. Delta C is upward deflection at C, and again there cannot occur an upward deflection at C. Therefore, we'll cancel 5, row 5 column 5, and theta C will also occur because this is a roller support and there will be some rotation at this point. Okay, therefore we won't cancel it out again. So now what we are left with is these 4 elements here, these 2 elements here, and these 2 elements here. We'll separate them out. 4 6 4 6 4 6 equal to this, and we just need to now simply find theta B and theta C using our matrix concept, or you can just multiply these and equate them with these two and solve the simultaneous equations, which is very simple. Okay, and we get theta b equal to minus 32.55 by EI radians. Units are very important. And theta c equal to 49.61 by EI radians. Okay, now after we have found these two, that is theta b and theta c, the deflections, these are basically a decay. Okay, the unknown decays. If you ask me the decay for this mean, then it is 2 because we just need to find the theta b and theta c, and these two we have found out. Now we need to find the reactions. Final step to find the reactions: R equal to K into delta minus AC. K is the total stiffness matrix, D is the deflection or the displacement matrix, and AC is the combined load matrix. And this, how did I get this particular equation is from this, from the previous equation, that is k into delta equal to AC. I just brought AC on the left hand side, which will become minus, so k into delta minus AC equal to my reaction matrix, and we'll substitute them here. This is the K matrix, the total stiffness matrix, into my displacement matrix, which is delta A is 0, theta is 0, delta B 0, theta B we just found out in previous step, delta C 0 and theta C we found it in previous step. So we need to substitute them here, and rest all others would be 0. Minus AC, that is my combined load matrix. We need to simplify this whole equation now, and I hope you know how to multiply the matrix, that is this row, first row, and this column minus this element. And if you see, then only these fourth and sixth element will get multiplied, rest all are 0, so the multiplication will obviously be 0. So you just need to multiply the fourth element here, 6ei by 9, into this fourth element, and sixth element into the sixth element. Now sixth element here is 0, so again this will result into 0. So only thing you need to multiply is 6ei by 9 into minus 32.55 by ei minus minus 59.26, and you will get here 37.56 kilonewton. Now this is in order VA, MA, VB, MB, VC, MC. Again, the order is similar to how you have numbered your forces. That is, since this is 1, the upward force was numbered as 1, therefore the upward reaction will be first, then comes the moment. Reaction, moment, reaction, moment, reaction, moment, reaction, moment, reaction, moment. This is how you need to number them. And VA you got as 37.56. Again, second row, this column, so fourth element into this, sixth element into this, fourth element is 2ei by 3 into minus 32.55 by ei minus minus 35.56, you get as 13.86 kilonewton meter. Third row into this column minus the third element, so fourth element here is ei by 12 into minus 32.55 plus 12 ei by 16 into 49.61 minus minus 80.74, you get 115.235 kilonewton as VB. Then again here 10 ei by 3 into minus 32.55 by ei into, I'm sorry, plus 4 ei by 4 into 49.61 minus minus 58.89, we get 0 kilonewton meter. And this is very important to just check whether you have done everything correct, because you need to get your 0, since we are allowing the uh, beam to get rotated at point B, therefore it cannot resist any moment, hence the moment has to be 0 since it is getting rotated here. Similarly, you will also get MC as 0, because we are again allowing the rotation at this point, because it is a roller support and roller support allows the rotation. Then we'll check for VC. VC is 12 A by minus 12 A by 16 into minus 32.55 plus minus 12 A by 16 into 49.61 minus minus 100, we get 87.205 kilonewton. And this again we'll get 0. 4 ei by 4 into minus 32.55 by ei plus 8 ei by 4 into 49.61 by ei minus 66.67, we get it as 0. Yeah, so these two are the checks that we need to take in consideration. But if you have done any mistake in writing the total stiffness matrix, or writing the combined matrix, or writing the joint load matrix, then you will get wrong deflections, that is theta B and theta C. And even by getting the wrong deflections, you will again get your 0 and 0. So this completely does not guarantee you that your whole sum is correct. These equations and these matrices are very important to write them precisely and correctly. Generally don't write them in points, write them in fractions, because fractions will guarantee you more precision in your calculations. Now once you have found out the reactions and these displacements, your other reactions and these are displacements, 37.56, 13.86 anti-clockwise. Now if I get any of these reactions as negative, Okay, suppose if I would have got 13.86 as minus 13.86, then it would have been a clockwise, because we have already set our convention here as anti-clockwise is positive. So since this is positive, this force has to be, or this moment has to be anti-clockwise. If this was negative, this would have been a clockwise moment. Okay, again upward force or upward reaction. So here I get 115.235 kilonewton, again 87.205, and everything else is 0. And this is how my beam gets deflected, with this being the theta b and this being the theta c. Theta b is minus 32.55 by EI, theta c is 49.61 EI. If you see here, then even this is in conformation with our sign convention. That is, we got here minus 32.55, which means that my beam is getting rotated in a clockwise manner. As you can see, this was my previous or my original axis of the beam, and now my beam has been rotated in a clockwise manner. Okay, this has been rotated in a clockwise manner, hence it is minus 32.55 by EI, that is theta b. And at joint C, my beam has been rotated in a anti-clockwise manner, hence theta c was positive 49.61 by EI. So these reference, what you take here, is very important, because my whole sum and all the sign conventions are based on these reference, or these positive forces that you draw in step 1. And this was the stiffness matrix sum. I hope you learned something valuable from this, and please like, share and subscribe, and press the bell notification icon for future videos.